Hello and welcome. This is going to be our lecture video for September 2nd and 3rd. Let's go ahead and get started. How would we solve an equation like this where we have an absolute value equal to an absolute value? Hopefully you've got your notes down. Pause the video, copy this one down, maybe try it on your own. Alright, in order for this to be true, these two expressions could either both be positive and then the absolute values wouldn't have to flip them to being positive. One could be positive and one could be negative, and then the absolute value would flip the negative one to being positive, and then they would match. Or the first could be negative and the second could be positive, or they both could be negative and the absolute values have to flip them both back to being positive. Regardless of what sign they start with, they always end positive. Now what we'll realize is that these two here are actually equivalent because I could multiply both sides by -1 and it would turn any positive equals positive into a negative equals a negative. And these two are equivalent. So although this looks like 4 scenarios, I only have to solve for 2 scenarios. Positive equals positive and positive equals negative. So let's do the positive equals positive case. So if they're both positive, then the absolute value brackets can be dropped. They don't have a job to do, so they go away. And then the positive equals a negative case, well, the first absolute value brackets are dropped, but the second set get turned into a negative parentheses, so they can flip the sign of this. And you only have to solve these two equations and you'll get all of the possible answers. So let's finish solving this one. Move the variables first. A minus 1 equals 4. Then move your constants away from the variable. A equals 5. And then over here we got to distribute that negative. 3a minus 1 equals negative 2a minus 4. Move our variables. 5a minus 1 equals -4. Add 1 to both sides. 5a equals -3. Divide both sides by 5. A equals -3 fifths. And that's how we deal with absolute value equals absolute value. Alright, goal for today is to graph inequalities containing an absolute value on a number line. So we're putting together multiple things we've looked at so far, inequalities and absolute values. And this can be a really useful way to describe tolerances or ranges. So we have like an average and then a tolerance, like a plus or minus. Very common thing we see in our day-to-day lives. Alright. So here we go. Our first instance where we're combining absolute values and inequalities. We want to graph the absolute value of x is less than 5. So here's what we're going to do. We are still going to split this into a positive and a negative case. Alright, so I'll just say positive, negative. So we'll say that x is a positive number, so the brackets don't have a job to do, they can just go away. X is less than 5. In the negative case, well, the brackets do have a job to do. They've got to flip that back to being positive, so they turn into a negative parentheses. So negative parentheses, x is less than 5. This side over here is already solved, but this side over here is not. We need to divide both sides by -1. I just divided by a negative, so I need to remember to flip the direction of my inequality. Alright, so I put a box around both of these, but I actually don't know if I should say and or until I graph them. Alright, so let's graph this first one. I go to 5, I do an open circle arrow going to the left. For this one, I go to -5, open circle arrow going to the right. These are going to connect to make a line segment. So that means that this was an and type all along. And this should make sense in order for this to be true, we need to pick a number that's less than 5 and more than -5. Because they're intersecting, if we made this an OR, then we would keep all of the numbers, and then you could pick a number like 6, but we know that that doesn't work because we can see absolute value of 6 is not less than 5. So it was an and all along. And with the and inequalities, then we can rewrite them like this. We can say -5 is less than x is less than 5. All right. What have we got? The absolute value of x is greater than or equal to 4. Well, let's split this into the positive and the negative case. Positive case, we're just going to drop those brackets. X is greater than or equal to 4. Negative case, we get negative parentheses. X is greater than or equal to 4. Divide this one by -1. We get x is less than or equal to -4. Now what does this look like on a number line? So I'm going to put my important values on there, -4 and 4. But for this first one, that's a closed dot at 4, arrows going to the right. This one's a closed dot at -4, arrows going to the left. These diverge, so this was an OR type all along. And once you get good at these, eventually you realize when it's a greater than, it's always an OR. When it's a less than, it's always an AND. But that's kind of a hard rule to remember. It's easier to just graph them. If they diverge, they're going to be an OR. If they intersect, it's an AND. All right, a little bit more challenging. Here we've got some operations inside and outside of the absolute value. Our approach here is to first isolate the absolute value. So we want to isolate the absolute value. So that means adding 5 to both sides. At the very beginning, absolute value of 2x plus 2 is less than 20. Now we can split this into the positive and the negative case. In the positive case, we drop the brackets. 2x plus 2 is less than 20. In the negative case, comes in negative parentheses. Solve them separately. So -2 minus 2. Divide by 2, divide by 2. X is less than 9. Here I'll distribute in the negative. Negative 2x minus 2 is less than 20. Add 2, add 2. Negative 2x is less than 22. Divide by -2, divide by -2. I just divided by a negative. I need to remember to flip my inequality symbol. All right, and let's see if these intersect. So at -11, I want an open circle, arrow coming this way. At 9, I want an open circle, arrow coming this way. These two intersect, so they're an AND type, which means that we can go ahead and write it as a single line inequality. -11 is less than x is less than 9. That. And let's talk about double checking real quick. I could pick a number in the middle here. A really convenient number that's in the middle is 0. Let's see what happens when I plug 0 into this. So this term goes away. That's just a 2. Absolute value of 2 is 2. 2 minus 5 is -3. Is -3 less than 15? It is. So it checks out. All right, let's talk about Goldilocks and the 3 bears. All right, what does Goldilocks find when she goes into this mysterious cabin in the woods? Well, a variety of things from chairs to beds, but she also finds porridge. Now, Goldilocks is very particular about her porridge. We're going to say that she wants it to be specifically between 86 and 102 degrees Fahrenheit. All right, any colder, then it's too cold. Any warmer, it's too warm. right in between, it's just right. And we'll say inclusively. So if it's exactly 86, she's still okay with it. All right, how do we represent this with a compound inequality in a graph? So I'll start with the graph. Here is our number line, which represents temperature. We want everything in between here. How would we say this? X must be greater than or equal to 86, and X must be less than or equal to 102. It can't just be one or the other, or else that would be all temperatures. All right. Now can we represent that same information with an absolute value inequality? It looks like when I created this diagram, I actually used open circles. So just notice that changed. Here, I don't want it to change. I'm going to fill those in. Okay, so I did fill in something else extra here, and that's the midpoint. Halfway between 86 and 102 is 94. How could I find that if I wasn't sure? Well, you can just average the two. 86 plus 102 divided by 2. That becomes a 188. 188 divided by 2 is 94. All right, so I'm just going to write that as a formula. It's min plus max divided by 2. All right. Now there's another piece of information, which is the tolerance. This distance here, we're going to call that the tolerance. And to figure that out, we just have to do the maximum minus the midpoint. 102 minus 94 is 8. So here we'll write that right here. This distance is 8, and then we can double check that this distance should also be 8 if that's the midpoint. And there is a formula to find that, and it's very similar to this one. It's max minus min divided by 2, because it's the difference here divided by 2 to split it into the two tolerances that make up that whole difference. Okay, so if you like formulas, you can do it like this. I like to just think it through with the diagram. All right, so now that I know the tolerance, I can set up an absolute value equation like this. I don't want the difference between x and the midpoint to ever be less than or equal to the tolerance of 8. And that will recreate this graph here. Let me think about that. Let's double check this. So if we split this into the positive and the negative case, x minus 4 is less than or equal to 8. Add 94, add 94. X is less than or equal to 102. Yep, that's part of it. And negative x minus 94 is less than or equal to 8. Negative x plus 94 is less than or equal to 8. Minus 94 from both sides. We get negative x is less than or equal to negative 86. Divide by the negative 1. X is greater than or equal to 86. Yep, we get both halves of it when we solve that. So the formula for this one, when we want to create intervals, is we can do the absolute value of x minus the midpoint is less than, we'll just leave it as the less than. You can add the or equal to if you want to include the endpoint, the tolerance. So whether or not that is the or equal to is question dependent. That's how we can create whatever interval we want on the number line. It's just using this. All right, write a single inequality with an absolute value to represent this graph. So we got to find the midpoint. The midpoint is 3. We We got to find the tolerance. The tolerance is 1. So plug that into our handy formula. X minus the midpoint is less than or equal to, these are closed dots, 1. That there should recreate this graph. All right, I'll embed a few more questions here. That's the end of this lecture video. Have a good rest of your day.